Hello, everyone. Today we are going to be learning about types of forces and Newton's laws. So we've already talked about motion and some of those different parts and pieces like speed, velocity, and acceleration within motion. We've also talked a bit about gravity, friction, and pressure. Today we're going to be looking at types of forces, which, hint, hint, we've already started learning about a bit. And then we're going to be learning about Newton's laws of motion. Now, I like science. I get it. You may or may not start realizing it, or maybe you will in your head and you'll be like, I'm never going to tell my science teacher, but you can just enjoy it in your head. These laws of motion apply to literally everything in our daily life. It is the reason we are able to move. These laws describe how things move or how we can expect them to move. So let's get going on this rather than just me telling you about how cool they are, even though you probably just rolled your eyes about 4 times. But even if there's a small connection here, awesome. So first thing is on this paper, either grab this one out, or if you have a printer, print this out. If you didn't get this in class or you're someone who's fully virtual, you could recreate this paper on like blank paper, but you're going to want to have this note sheet. So make sure you're filling this out, and then you're going to need to turn this in so we see, oh, yep, you got this. So first thing, please put your name on here. Please put the date that this is due and then what hour you have science class. It says it right at the top. What we're looking to learn about today is that I can apply each of Newton's 3 laws of motion to situation in my daily life. We got to learn about them before we know how to apply them. So at any time in this video, go ahead and pause if you need to write anything down or refer back to it. The slides are pretty much in the exact outline that are on here, so you just have to fill them in as we go. So heading over to our slides. So a force. What is a force? It is simply a push or a pull. At the most basic definition, a force is a push or a pull. Anytime you're changing the motion of an object, you use a force. It can be changing the speed, the direction, or both. If we're talking about speed with a direction, that's a vector quantity and its velocity. I see a few of you might be rolling your eyes. It's okay, we'll keep going. But a force is a push or a pull. So what are some of our types of forces that we have? Our first one is a contact force. This is when an object pushes or pulls another object by actually touching it. So this is like, I've got a few different things I'm going to need for demos. If I push my little meter across my desk, contact force. If I'm pushing anything, contact force. Other types of forces. Gravity, force of attraction between two masses. The strength of the gravitational force depends on the object's mass. Now, this is one that we had just learned about talking about how gravity works and how that exerts forces on other things. Gravity is not a contact force. It's just because when something gets super, 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 super massive, it has an attraction that pulls everything to it. Now, anything that has mass, remember, has gravity. So even you, right now, you have a teeny, 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 tiny bit of gravity that you're pulling everything towards you with. The thing is that it's so small that you're not pulling anything towards you, actually. The Earth, on the other hand, though, is so big that it's pulling us to the ground. That's why we don't float away. And then the other one is friction, this is the one that's resisting motion between two surfaces. Friction is the one where if I like slide my pointer across here, it's going to stop. It's not going to keep going, and it's because there's friction. Yes, I can feel this, and it feels very smooth. My desk feels very smooth, but there is friction that exists, which is why it stops eventually. We're going to learn that we've got an object should move in a straight line unless there's an outside force. The outside force is friction here. So, continuing then. Forces are vectors. This means they have both direction and magnitude. Did some of you just start playing that clip in your head? If you didn't, we're going to be catching a glimpse of that here real quick. But forces are vectors. They have to have a direction. They have to have a magnitude, meaning we need to see how much force or what is the amount of force being pushed on something, and then the direction as well. Force is measured in newtons. So how many newtons of force are being applied to an object and in which direction? So if I move back to my little slider, I'm applying a force going towards the left here. Question though, velocity uses a vector, so does force. Does this mean they're the same? What is a vector really representing though? What is it on a graph? Remember, an arrow or a vector is just a mathematical symbol that represents direction and magnitude. Just as Vector, the villain from Despicable Me, tells us, a vector is just a mathematical symbol. It's considered a vector when we talk about velocity because we need both a direction and magnitude. So it's a vector quantity. Force is a vector quantity, meaning we both need to have both direction and magnitude. So these are, a vector can be more than one thing, but on a graph, it's simply just saying it's an arrow. Because an arrow shows us the distance, and then how long it is going to tell us how much force is going in that direction. So really, the length of the arrow just tells us the amount and the size of the force. So if you look at some of these here, there's ones that are like shorter versus longer. The shorter one is showing us a smaller force. The longer ones are showing us a larger force. I'm going to go into present mode here because we need to head over to... Oh, there's our friend. So, vector quantity, because I'm going to make sure you know what a vector is for the rest of your life, even if you roll your eyes 4 times.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
Remember, the last part's just for funsies.
Piranha gun! Oh, yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Doing a demonstration. Oh, ah! It's so difficult sometimes to get the line back inside.
So a vector, remember, it's just like Vector said here, that Vector the evil genius. It's a mathematical symbol that represents both direction and magnitude. So our size and directions of forces. A net force, this is saying the overall force acting on an object when all the forces are combined. A balanced force shows that our net force is 0, which is the same as really having no force. If it's, so here's an example. If we have like the same length of arrow, they're just in opposite directions, they're going to cancel each other out. If we have an unbalanced force, it's going to change the motion of an object. So that's like if we have a larger force on one side and a smaller force on the other, we're going to have motion. This is kind of like if we think about friction and your car going down the road. When you first start your car, well, not first start, as you're going along, your car is able to keep going, but there's always friction pushing back on it. But it's an unbalanced force that's keeping your car going. I've got some little helpers here. If I have, so usually I have like this giant cart and I have some students go on each side, but we're going to represent the different forces here with some of these things. So if I have a balanced force, it would be like we say, there's no motion. If I have 1 and 1, they basically cancel each other out and we're not going to have any motion. Okay, I get you're like, Miss Moronic, it's not going to move because they're plastic clips. I get it. Use a bit of an imagination with me, okay? So if there's 1 and 1, or if there's none at all, this isn't going to move because there's the same amount of force on each side. There's no movement. Now, if I stack one of these sides up, theoretically, if these were able to all push or pull, I've got 4 to 1. which means if these are all pushing in this direction, yes, this guy's going to do what he can, but he's really only going to counteract one of these clips. So basically, a net force is like saying, you know what, I've got 1 and I've got 1. So it's like saying I've really just got 3 newtons of force heading in this direction. When it's a balanced force, like I could have 2 and 2, but because they're equal, it's not going to move. So that's the difference between a balanced force is like, it's basically like there's nothing because they're all going to just cancel each other out. So it's basically like there's nothing. Or an unbalanced force, we're going to have more on one side than the other. And yeah, we're going to cancel out as much as we can, but we're still going to have more at the end of the day. So heading back over here. So forces on moving objects. Balanced forces cannot change an object's speed or its direction. So even if it's already even if it's already moving, if there's a balanced force on something that's already moving, nothing is going to change. It's going to keep moving at its same speed. If it's an unbalanced force, it can change the object's speed or its direction or both. I know, it's crazy, right? But the balanced forces, they're just not going to change its motion. So yes, we could say that this M, maybe for some reason, maybe if we get Mater out here. So we've already got Mater who is moving at like, say, 1 meter per minute, okay? If Mater was already moving at 1 meter per minute and I have the same force, he's gonna keep going at the same rate. Now, if I have 2 of these guys that come, and so Mater's going, and then for all of a sudden we've got extra, he's gonna go faster because there's more force acting on it. But if the balanced forces, he would just keep going at his same rate. Like there's not going to be any change or extra. But if there's more, like, whoo, now we got double, he's going to speed up in that direction or slow down, whichever it's going to be. But at the end of the day, balanced forces will not change the object's speed or its direction. An unbalanced force is going to change the object's speed or its direction, or both. So we're getting into Newton's first law of motion. This is on to the back side of that, and please write down the laws of motion when we get there. First, I do have a little bit, though, about Isaac Newton. So, Sir Isaac Newton, he lived in about the mid-1600s. He built on the ideas of Galileo Galilei. And he was looking at that objects only seem to stop moving if there's a force acting upon it. So Newton's first law, please write this literally word for word. This is something you want to know, Newton's first law. There's like 3 that you're going to want to know pretty much word for word. This is one of them. So Newton's first law, an object at rest stays at rest. An object in motion stays in motion and in a straight line unless acted upon by an outside force. Pause this right now if you need to write that down. There's 2 lines there because I expect to see that completely written out. No abbreviations, no missing anything because you need all of this. An object at rest stays at rest. An object in motion stays in motion in a straight line unless acted upon by an outside force. What is this saying? If I have Mater sitting here, an object at rest stays at rest. An object in motion should stay in motion, but there is a reason why it stops here, and that's friction, which is an outside force, which is what we said. But when I roll Mater across, Mater goes in a straight line from the direction I initially started. I don't expect to push Mater off and then all of a sudden he's going to turn. I expect when I push him, he's going to stay in that straight line. He's not going to turn. That is our first law of motion. It seems really simple. Yes, it's a little wordy, but it is that simple. Just an object at rest stays at rest. An object in motion stays in motion and in a straight line unless there's an outside force. So the only reason that Mater stops moving here is because of friction. It could also be Mater runs into my hand. It could be that there is bonk, I don't know, something. Outside force is stopping Mater, but Mater is going in a straight line otherwise. Or if Mater is just sitting here, I don't expect all of a sudden that Mater's like, woo, starting to move around. Object at rest stays at rest. Object in motion stays in motion in a straight line unless acted upon by an outside force. This one here is friction. We can have close to no friction scenarios here on Earth, but everything in Earth always has some friction. Inertia. So this is the resistance of an object to change in the speed or the direction of its motion. It's closely related to the mass of the objects. So make sure you jot down inertia. Now, inertia, this is one that I like to think about, especially around this time of year. Is it easier to stop or turn an empty wagon? Is it easier or harder to stop or turn a full wagon? Typically, if I go to, like, say, a pumpkin patch or something, when I first start out with my empty wagon, it's pretty easy to pull. Once there's pumpkins in it, it gets harder to pull. Here's another example. So my family, growing up, how my parents got paid was every 2 weeks is when they got their paycheck. Every 2 weeks, then we'd go grocery shopping. When we'd go grocery shopping for 2 weeks, as you maybe can imagine, we had a pretty full shopping cart that we needed to fill up because we went to, it was called Woodman's in Janesville, where they've usually got some better deals on food. So that's usually where we went, and that's where we shopped, just so we could get a little bit more for a little bit less. As we're shopping, though, down the aisles, we're pushing. And when we first start out, super easy to push that cart. But then as we're shopping, my dad is absolutely addicted to Diet Mountain Dew. So we probably have like at least a 24-pack of that on for the next 2 weeks. We probably have 2 to 3 gallons of milk. You guys are like probably thinking, okay, this is starting to get heavy. We probably have like a flat of water we've had to put on there. If it was, we quote unquote a big week where we had to spend more money because we had to get like dog food, we got that on there. That's getting heavier. Maybe we have a lot of canned goods that we've added to there. It's making the cart heavier and heavier and heavier. So when I started out, it was really easy to push that cart, turn the cart, any of that was just fine. As it gets to the end, it's hard to get that cart going. And once I get that cart going, I don't really want to stop it. If my parents are like, oh, let's quick go down this aisle, I would like roll my eyes and like, seriously, we need to turn down that aisle? We were just down that one. Or they would always run into a few of their friends and it's like, I just got this cart moving and now I need to stop it, because it's hard to move that cart once it gets full. Now, maybe you have another idea that you can think of. Maybe if we're thinking about football. Okay, what I'm saying is it easier or harder to tackle a bigger football player versus a smaller football player. I'm not talking about like skill level, like if you're a more skilled person. I'm talking about size-wise. Is it easier to run up to someone who is a smaller player and knock them over? Or, in general, is it easier to run up to someone who's a larger player and knock them over? I'm going to say, if I'm going to be using, say, 100 newtons of force, I'm going to be able to knock down the smaller football player a lot easier than I'm going to be able to knock over a larger football player. That's why when you look at some of the people that are on the football field that are doing the blocking, they're not the tiny guys, because you want a bigger person, so it's harder to move. Yes, a lot of them have a lot of muscle, which means they have a lot of muscle mass, but it's harder to tackle or it's harder to push over a larger mass. It's inertia. An object wants to stay doing what it's doing. My mater here does not want to start moving right now. And once I put mater into action, mater would rather keep going. Oh, my cord caught it that time. Mater would rather keep going, but friction is what stops it. So inertia is just saying an object that it just wants to, it's the tendency of that object to want to stay doing what it is doing. If it's already in motion, it wants to stay in that motion. If it's not in motion, it wants to stay at rest. If it's already going in a straight line, it wants to stay in a straight line and it doesn't want to turn. Yes, you can do any of those things, but you need that outside force. We do have something called centripetal force, which is also related to the first law, and a centripetal force is any force that keeps an object moving in a circle. Remember when we talked about roots and prefixes? Centri, center, pitis. It's the derivative of Latin to seek, but does it look like Circle. If you're hearing something about a center or a circle, that's because centripetal force has those common roots and prefixes. So that's the way you can help remember centripetal force. It's going in that center. Centripetal force, it's what keeps an object moving in a circle. Like if you're on a roller coaster and you go around a circle, you're kind of smushed into your seat because your roller coaster is wanting to keep you going in a circle. Yes, inertia wants you to keep going in a straight line at each of these seconds, but centripetal force keeps you going in that circle. This is kind of how gravity works, is that it's wanting to keep that object going in that circle because it's always applying a force towards the middle of that object. So as the moon moves around the earth, let's see. If I've got, okay, I get these don't look like the moon and the earth. Like, go ahead, roast me later. But if I have something that looks like this, and then I've got my moon going around the edge, the earth is always applying a force on the moon straight to the center of the earth, which is why my little moon here keeps going around the earth. That's centripetal force. So, continuing. Oh, this is where I don't know how well it's going to work. I might be able to make this work pretty well. Centripetal force we can also add or show as something going in a circle. So usually I have this fuzzy dice that I whip around my head and then get going in a circle and then I let it go. Let's see if we can get it to go with a paper clip. So if I get my paper clip going and then let it go, you're going to notice that it goes in the exact, it's going to go in a straight line of where I last, there we go. It's going to go in a straight line from where I let it go, let it off. Because it always wants to be going in a straight line due to inertia, but the centripetal force is what's keeping it in a circle, keeping it going around. When that circle's broken, off it goes. So, back to here. Force and mass will determine acceleration. This is Newton's second law of motion. Okay, you don't need this whole long bit. You need this next bit, the part that says write down. Please write down both force equals mass times acceleration, and then in parentheses go F equals m times a. You need to pause this video so you can do that. Please do that. But we're looking at these, that force is equal to mass times acceleration. Now, what does this mean exactly? If you haven't paused the video to write that down, please do that. I'm going to move on to my next bit here. Because before we go too far, I want you to have the Newton or the units. These are the SI units, which means these are the standard use units that we are going to use when we are talking about force equals mass times acceleration. So force is in newtons. Please write the word Newton and then a little n in parentheses. So when we need to abbreviate it, it's just n. Mass is in kilograms. It's kg. And acceleration is in m per s squared. Did we just learn about acceleration in our last unit? Interesting. It's like they connect or something. Also, if you want to have just a little joke, little sciencey joke here, may the mass times acceleration be with you. So this is a May the 4th joke, but may the force as well. May the force be with you. Force is equal to mass times acceleration. I know, you're laughing so hard you can barely keep yourself together. So, on Newton's second law, force is equal to mass times acceleration. So, if you have a small force, you're going to have same mass. A larger force is going to give you more acceleration because you have more force to move that amount. Now, if you have a larger mass and the same force, you're not going to have as much acceleration. It's basically saying that regardless of how any of these work, the force equals mass times acceleration is always going to be true. If you have a small mass and you're giving it acceleration, you're going to have a large force. If you have a larger mass with some acceleration, you're going to have a larger force. Like you're just basically dragging and dropping numbers into here a little bit. Let's see. Let's go back to here. So if I have a mass about this big and I push it with just a little bit of force, not very much acceleration. If I've got this and I give it a lot of force, right, Mater's got a lot more acceleration. Now, if I change the mass of objects, so if I'm going to try and have 2 here, so I'm going to try and give it a little push and this one a little push, Mater's going to move a lot more than my cup because my cup is a lot heavier than Mater, right? So they all play a role into each other. We're going to definitely do more math with this coming up, but that's kind of a first little introduction. They all relate to each other. And then we've got our last law, which is Newton's third law, saying forces act in pairs. For every action, there's an equal and opposite reaction. Everything I've done today has shown all 3 laws of motions. There's just some of them just show one thing a little bit better than other. Please write this down word for word. For every action, there's an equal and opposite reaction. So those 3 things to memorize eventually, but we're going to use them so many times in this unit, you'll just memorize them by use. And if you're like, I will not, Miss Moradic, well, you probably still are going to figure out what they are. It's just going to kind of be secondhand that you're going to have to know these. So the first law was for every action an object in motion stays in motion in a straight line. An object at rest stays at rest unless acted upon by an outside force. I think when we actually wrote it down, we said an object at rest stays at rest. An object in motion stays in motion in a straight line unless acted upon by an outside force. The second law is force is equal to mass times acceleration, and our third law is for every action, there's an equal and opposite reaction. What does this mean? It means there's always an action and a reaction force. So every time there's any contact between anything, every time I've pushed Mater also pushes a little bit on my finger. In fact, I can tell you that after pushing Mater and all these things so much today, the tip of my finger is starting to hurt a little bit. It's because of this action and reaction force. Mater is applying a bit of a force because remember, an object at rest wants to stay at rest. So as I'm pushing on Mater, Mater's also pushing on me a bit because Mater doesn't want to have to move. So if you're both on roller skates, and hopefully we can do some of this lab or we'll be able to at least demo part of it. If 2 people are on roller skates and you push away from each other, you're both going to move some. How cool. The third law, when one object's exerting a force on another, the second object exerts one back. So if you're like on a skateboard, you push on the ground pushes up at you. This works because you're able to move forward. If the ground didn't push back, you wouldn't go very far. You might be able to think of this in terms of if you've ever been on something really soft, sandy, like mud, and you go to push off from it, not much happens because it doesn't have enough force to exert back on you. Another one, a balloon. You let the air out of a balloon. The balloon goes forward, the air goes backwards. Another favorite one that I have, and the reason I mostly have my Mater out, is we can do an example here right now. So I have Mater and I have my Gator. Mater has done this experiment a number of times. So what we can expect to happen if I throw or make these run into each other. Reminder, objects in motion want to stay in motion in a straight line unless acted upon by an outside force. I think we're going to have some outside forces here. Also, you're going to notice that one of these are heavier than the others, so there's going to be applying a different amount of force on each other. But the biggest is you're going to see an action and a reaction. So let's see how well I can do it. It usually takes me a few times to get it quite right. So you can probably tell Mater is the heavier one. So that time it worked out. There we go. But they break apart. Now Mater is the heavier one. And this one is my Gator is able to take more, it moves more because it's lighter. That is our second law. But when they hit and then move up, oh boy. when they hit and move apart from each other, Mater's tooth makes it a little hard that they go kicky-cockied. But they break apart. They hit and then break apart. This is the same thing that happens like if there's a head-on collision of vehicles, when they hit, they break up, they go apart because they both give each other energy. They both smack into each other and then break apart because there's that action and reaction force. Now, when there's a car that there's like a crash that's like this, that usually doesn't happen because all of the force is going in this way and it's trying to change the direction of this vehicle that was already going in this direction. So those are kind of some of our big things. I do have one more that kind of wraps it up here. So if we think of it in terms of like a kangaroo, first law of motion, this kangaroo has jumped, setting itself in motion. If no other forces were acting on it, the kangaroo would continue to move through the air with the same motion. Instead, gravity brings the kangaroo back to the ground. Second law, the larger kangaroo does not have as much acceleration as a less massive kangaroo if it used the same force to jump. However, the more massive kangaroo can increase its acceleration by increasing the force of its jump. And then the third law, a kangaroo applies an action force on the ground with its powerful back legs. The reaction force from the ground can send the kangaroo as far as 8 meters or 26 feet through the air. What I've got at the end of these slides is there's a number of different really good videos that in class I show all of them that I possibly can, and then I kind of just sprinkle them out throughout the unit. I would highly recommend going back and watching these or catching these. There's the NFL, there's the first law, Newton's first law in space and here on Earth. So if you want to look these up on YouTube, or we'll try and put them onto Google Classroom. This one is with the European Space Association. There's some different ones with like the seatbelts, Newton's second law. So the NFL has a really cool set of 3 of them. And then that ESA that you saw back, let's see, where was that? It was back a few slides. The very first one I had, they've got a first, second, and third law. So all of these would be really good ones for more examples because they just have more and more and more examples going over these. But at this time, once you are done getting all the notes, go back, make sure you have everything, make sure this looks nice, and then make sure you take pictures to submit this or get this to your teacher in some way. Otherwise, if you have questions, please ask your teachers. This is our first time we are looking at these different forces and laws. We're going to keep learning about them. This is just kind of our first bit. So if you have questions, please let your teacher know. Otherwise, have a great day, guys. Bye.